Hi everyone, this is Maverick Paul, the Chemistry Guru. Now in this video, we want to discuss the suggested solution for 2021 A-Levels H2 Chemistry, Paper 1, Question 13. Now question 13 goes something like this. In reaction 1, hydrogen reacts with gaseous bromine to form hydrogen bromine. The balance equation is given. In reaction 2, hydrogen reacts with gaseous iodine to form hydrogen iodine, and the balance equation is also given. For reaction 1, the rate equation is, the rate is equals to your rate constant 1 multiplied by concentration for your H2 multiplied by concentration of bromine power 1.5 divided by the concentration for bromine plus rate constant 2 multiplied by the concentration for HBr. So we notice this rate equation looks very complicated. Now for reaction 2, the rate equation is rate is equals to rate constant K multiplied by concentration for H2 and multiplied by concentration for I2. So this rate equation for reaction 2 looks a lot more familiar, and this is according to what we have learned in syllabus. Now what is correct about these reactions? So statement number 1 for the hydrogen and bromine reaction, formation of HBr slows down the rate of the reaction. Statement number 2, only the hydrogen and iodine reaction could be a single-step reaction. Statement number 3, doubling the concentration of the halogen in each reaction doubles each rate of reaction. So we want to determine which of these statements are correct, then we can answer this question. Of course, the topic tested in this question will be under kinetics. And again, the portion which is intimidating is my rate equation for reaction number 1. We actually don't really need to understand this very well. Later, when we run through the options, we will be able to deduce which of these statements are correct part by part. So let us talk about each of these statements. The first one, involving hydrogen and bromine reaction, formation of HBr slows down the rate of the reaction. Now what we can do is we can just simply make use of the rate equation for the reaction between hydrogen and bromine. The reaction is here, H2 plus Br2 to give me 2HBr, and the rate equation for the reaction between hydrogen and bromine, the rate equation is given here. You notice what we have is the HBr term is in the denominator, and therefore we can just apply this accordingly. When you are forming HBr, the concentration for HBr increases, and since this is in the denominator, when you have a bigger denominator, this will mean that the rate will decrease. So the statement 1 is true because when you start to form HBr, when you have a higher and higher concentration of HBr, the rate of the reaction is expected to decrease. So we actually don't really need to care so much about the other terms and what they represent, because really it is very, very complicated. So we just apply whatever that is mentioned in the option and we just deduce it accordingly. So involving statement number 1 is true. Increase in concentration of HBr will cause a slowdown in the rate of reaction. Statement number 1 is correct. Now moving on to statement number 2. Statement number 2, only hydrogen and iodine reaction could be a single-step reaction. Now, we have actually learned this under kinetics. We say that when I have a reaction, if it is a single-step reaction, then that single step must be the rate determining step or the slow step. In general, when we have an overall reaction, sometimes we have a few elementary steps. Then one of these steps will be the slowest step, or we call this the rate determining step. And that slow step will determine the rate of the entire reaction. It is like the bottleneck. So the rate of the entire reaction is being limited by the slow step or the rate determining step. Now, if we have a mechanism which is a single step, this means that that single step must be the slow step or the rate determining step. And this would also mean that all the reactants has to be involved in the rate determining step, because there's only one step involved. And therefore, if your hydrogen and your iodine reaction is a single step, all the reactants in the reaction involving hydrogen and iodine, all the reactants must be involved in that one step to give me the products. And this means that the coefficient for the reactant in my balance equation will correspond to the order of the reactant in the rate equation. Now again, this one we learned this under kinetics. We know that there's a relationship between the slow step and the rate equation, whatever number of species or the reactants that are involved in the slow step, the coefficient for the reactant is actually corresponding to the order of that reactant in the rate equation. So in the slow step, if you have one reactant A, this means that in the rate equation, this will be first order with respect to A. If in the slow step, I have 2A involved in the slow step, then in the rate equation, this will be order 2 with respect to A. So the coefficient for the reactant in the rate determining step will correspond to the order of the reactant inside the rate equation. So let us try to apply this idea for each of these reactions. We do this for reaction number 2 first because it is a little bit simpler. Now, if I consider the overall reaction for H2 plus I2 to give me 2HI, I'll have 1 H2 and 1 I2 to give me the product. Now, if this were a single step, then all the reactants must be in the rate determining step, and therefore the order of the reaction with respect to hydrogen will follow the coefficient. It will be order 1 with respect to H2, and order of the reaction with respect to I2 will also follow the coefficient. This will also be order 1 with respect to I2. So first order with respect to H2, first order with respect to I2. Therefore, when I write out the rate equation based on this as a single step reaction, so the rate equation will be rate equals to rate constant K multiplied by concentration of H2 power 1, which represents the order of the reaction, order 1, with respect to hydrogen, multiplied by concentration of I2 power 1, which represents the order of the reaction, order 1, with respect to I2. So if it were a single step process, the rate equation is supposed to be like this. This is the proposed rate equation. And if I look back at the rate equation that is given in the question, it is exactly the same. Your rate equals to K, concentration of H2 power 1, concentration I2 power 1. So this is possible. This process involving reaction number 2 is possible to be a single step reaction. Now, involving reaction number 1, H2 plus Br2 to give me 2HBr, what we can do is we can do exactly the same as what we have done previously. What if it were a single step reaction? Then what would the rate equation look like? And I know that if it is a single step, then all the reactants will be in the single step, and the order of the reaction with respect to the reactant will just be the coefficient for that species. So coefficient for H2 is coefficient 1, first order with respect to H2. Coefficient for bromine is coefficient 1, first order with respect to Br2. This means that if this were a single step mechanism, the rate equation would be rate equals to K, concentration of H2 power 1, concentration of Br2 power 1. This is the proposed mechanism if this were a single step reaction. Of course, when we look at the rate equation, the actual rate equation looks significantly more complicated. Again, we don't need to go down into detail, and we try to understand how do they get this rate equation in the first place, because it looks very, very complicated. So we do know that if I have two K terms, you notice I have K1, which represents the rate constant for probably one step in the mechanism, and I also have K2, a second rate constant term, which is suggesting that there will be another step which corresponds to step number 2, and the rate constant term will be K2. So this means that since I have two rate constant terms, K1 and K2 in this expression, so minimum there will be 2 steps for this mechanism. Again, it is a little bit complicated, and in syllabus we don't need to be able to interpret that, but based on what the question is asking, can this be a one-step or single-step mechanism? We realize that it is not possible, because if it were a single-step mechanism, the rate equation would look a lot simpler that we have talked about previously, and obviously the actual rate equation is different from what is proposed, and therefore your reaction 1, the reaction between H2 and Br2, cannot be a single-step reaction. Minimum, it will be 2 steps. And if I go back to statement number 2, statement number 2 is saying that only the hydrogen and iodine reaction can be single step, which is true. Only the reaction between H2 and I2 can be single step. The reaction between H2 and Br2 cannot be a single step reaction, and therefore statement number 2 is also correct. Now finally, let us consider statement number 3. Doubling the concentration of the halogen in each reaction will double each rate of the reaction. Again, what we can do is we can just apply and substitute the change in the concentration of the halogen into each rate equation. Then we figure out what will happen to the rate of the reaction. Reaction 1, the complicated expression, your rate, is equals to this big expression. We just focus on the concentration of my halogen. Concentration of Br2, you notice numerator, there's a Br2 power 1.5. Denominator, there's a Br2 power 1. So if you double the concentration of bromine, then we will expect the numerator, it will cause the rate to increase by 2 times to the power of 1.5, then divided by the denominator 2 times. So this definitely will not work out to be doubling the rate of the reaction. So it looks a little bit complicated, but we do know that if numerator times 2 to the power of 1.5 divided by the denominator times 2, then it doesn't correspond to doubling of the rate of the reaction. So reaction number 1 is not true. If you double the concentration of the halogen, I will not double the rate. So statement 3 is already wrong. But involving reaction 2, we are able to verify this because it is a lot simpler. The rate equation is a lot easier to interpret. When I double the concentration for I2, so this is first order with respect to I2, double I2 concentration, this will mean that the rate of the reaction will double. So reaction number 2, this is true. Double concentration, double rate. Reaction 1, it is not true. Double concentration, the rate doesn't double. This means that statement number 3 is wrong. Statement number 3 is incorrect. You notice again, the rate equation for reaction number 1 looks very complicated, but we don't really need to understand this that well. We just try to apply accordingly to whatever each of the statement is requesting, and we should still be able to answer this question. Now, finally, let us run through the options. We know that statement number 1 is true. We know that statement number 2 is true. And we know that statement number 3 is not correct. So therefore, the answer to this question will be option B. Statement 1 and 2 only are correct. Alright, so that was the discussion involving this pretty interesting kinetics question because of a very complicated rate equation. So if you have learned something useful from this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all for now. I'll see you next week.